Okay, so hi, this is Professor Ted. This is going to be an interesting series of lectures that I'm going to do over time that um, try to really bring the foundation of engineering mechanics to all of you. You know, statics, strength of materials, vector mechanics, physics, things like that, that can help you take what you learn in your textbook and in your classes and through lecture and really relate them to the real world. I've been an engineer, practicing engineer for 40 years, and I have a bachelor's degree in civil engineering and a master's degree in structural foundation engineering. Spent about 20 years in the utility industry, designing and constructing power plants, and then the last about 20 years in the consulting industry. So the real goal for me is to explain to you and get you working on a situation where you understand how to take what is going on with loads and be able to take those loading conditions and apply them correctly to a structure or to a piece of equipment so you can take all your design techniques and make them work in a safe and efficient manner for all of your clients and your owners and your employers and so forth. So these are the type of courses that could be used to help people study for the PE exam. I'm actually a PE in 18 states, and that's always been a big benefit to my career. If that's something you're looking to do, again, these courses, I think, these lectures, they're going to be based on about 10 minutes long, and they're going to look at a different topic and be able to take those and utilize them to help you study, to help you understand concepts, to help you look at design and build your career from there. So here's an example right here of statics. We'll start out today with some statics work and understanding that statics really is vector mechanics, and it's really the response to how bodies are going to react to a force acting on them, right? So what we're looking at now is we're really looking at this right here. Statics is the study of bodies at rest. And when we get into some of the more mechanical type of work, kinematics and kinetics, when we're talking about things moving, we'll understand how friction comes into play, how heat can come into play. But what we're really talking about now is we want to look at how forces are distributed to a structure through external loading conditions. You need to be able to go out as an engineer when there's for example, a construction crew on site and they're waiting for some answers for them to be able to keep working on a job and be able to understand what you see in the field and be able to take that mentally and apply it back to either a 2D or 3D condition that you might have learned as a student and then as a working engineer. So remember the history of statics is that they needed a lot of these principles in order just to construct things hundreds or thousands of years ago using this stuff right here, using levers and inclined planes, pulleys, things like that to overcome friction. We need to understand that there's a fundamental quality to mechanics, and those qualities are space, time, mass, and force. Now, if you're like me, when I first started taking these type of classes and learning about mechanics of materials, I had an issue with understanding the difference between mass and force. So we're going to talk a little bit about that today, but mass is something that occupies space. It's a measure of inertia. Okay, we'll get into that more as we go along. But force is actually the action of one body on another, pulling or pushing. So that's why force has a gravity component to it. You can have a body of a certain mass and it will have a different weight or a different force underneath different gravitational types of constants. Now a particle, we're going to start, as we talk about statics, we're going to talk about particle mechanics. And a particle has no mass, no size or shape. It's concentrated at a single point, which allows us now to say that there's no rotation. If you've studied statics already, or you're going to start studying it, you're going to learn about things called moments. And you can have torsion, you can have things twisting, you can have things bending. But in the case when you're working on a particle, that is not the case. We don't have any of that rotation. In our first law of motion by Newton, we know that the force on an object is a mass times its acceleration, and that acceleration is the acceleration due to gravity. So Newton's law of gravitation, so we're talking about this law right here, that's what we're talking about, is the force is equal to the gravitational constant times the mass of one object times the mass of the other object over r squared, which is the distance between the centers of the two bodies. So if you're talking about the fact that it's a, if you're talking about an object on the surface of the Earth, then that r is the radius of the Earth, right? So we have various constants, the universal gravitational constant in both the SI units as well as the US units. When we look at them, we can really simplify that down and say that the weight of something is equal to its mass times g, where g is the gravitational acceleration of the Earth in this case. So let me show you here. So this equation, the weight, is equal to the mass times gravity, and this g right here comes from here. That g is either 32.17 feet per second squared in the English units, or in the SI units you have 9.81 meters per second squared. Very important to realize that when you're looking at mass in the US units, mass is in slugs, pounds, second squares over feet. And in the SI unit, mass is in kilograms, but weight or force in the US units is pounds, and newtons are the force in the SI units. This is something that people, when they're first learning, have a real issue with. So when you look at the fact that in every case, your dimensional considerations mean everything. You have to make sure that if you're working in slugs, you're working in slugs and not in pounds. Here's a good example. This is a beam, all right, and let me just take this here. We have an end condition and an end condition that we will discuss in more detail, but the beam has a span of L. L goes from one support to the other. We have a load, okay, some block W, that's creating a force of F. So if we know that the mass of this block W is 30 slugs, and yet the acceleration in whatever area it's in is 50 feet per second squared, right? It's not 32.1. In this case, we're using 50. We know that 30 pounds second squared over feet, that's 30 slugs, times 50 feet per second squared, the second squared, okay, so this cancels with this cancels with this, and you get pounds. That's what we're looking for. We're taking something in slugs and we're putting it in pounds. We have to make sure we have these units right, and we'll do a lot of examples that show these units. Now, that's all I'm going to talk about today for this first lecture. We'll start next time talking about significant figures, and then we're going to go into talking about, well, you know what? Let's talk a little bit more. Might as well. We'll talk about significant figures now. Always remember that the accuracy greater than 0.2% is seldom achieved in design design arenas now. So your safety factors, if you take a look at this over here, this is what significant figures means, right? There's 3, 1, 2, 3 figure passed to the right of decimal point. In this case, there's 1. So if you multiply those together, this is 3 significant figures, but really you're only accurate to 1 significant figure because that's the smaller of the two between between 1 sig fig and 3. Now, if you take that and if you look at what that percent accuracy is, if you take 106.2 minus 106.194 over 106.194, you'll find that that's 0.006%. That is very, very good. So what I'm getting at here is check this out. Look, if you don't need to be to 3 significant figures, because even when you use 1 significant figure, it's still within 0.06% of the 3 significant figure number. So don't worry about all those figures out there. Significant figures make it quicker on your calc, and you can have it just as accurate. Okay, so let's pick up with this next time. We're gonna start with looking at concurrent force systems and really start getting involved in it. So as you're watching these things, I really do, request that you leave some questions that you have at the bottom of these videos, because I'd like to look at your questions and answer them. Like I said, I've been in this field a long time, and I want to help you all be good engineers. I want you to do very well in school. I want you to be able to use these to recertify yourself on exams like PE exams if you're studying for registration, and I want you to be able to use these for design in the future. So thanks a lot. Take care.